Okay. Hello, everybody. We have Let's wait. Okay. Hello, everybody. My name is Benjamin Diaz. I am a cloud engineer at Openstack. The following presentation, it's about a project we have been tinkering with at the company that's called Microclouds. The presentation is called Microclouds for Fragmented Markets, getting Openstack everywhere. So let's begin by saying, what are fragmented markets? The definition is a marketplace when there is no company that can exert enough influence to move the industry in a particular direction. The market consists of several small to medium-sized companies that compete with each other at large enterprises. For example, most of Latin American markets. So in practice, what this means? Let's take, for example, Chile. In Chile, we have several network fragmentation issues. We can see that the round-trip time between countries in the region is average like 180 to 40 milliseconds. That's a lot. So it makes sense that clouds need to be deployed in-country to serve in-country customers. So we are talking about small markets where getting Openstack is more difficult than in countries like the US or Europe, because the initial costs are great and budgets are a lot smaller. So here we can see that around 80% of Latin America requires small deployments. That means that the costs and the benefits for these companies, when talking about starting with Openstack, generate a number of problems, because they need to train people, they need to buy nodes, buy hardware. So trying to answer that situation is what we will be discussing. So let's talk about what we call microclouds. So the traditional cloud involves a several of compute, network, and storage nodes, but also all the data plane controls, the data controlling facilities in Openstack, the controller services, the metric services, the monitoring services. So we thought, how about sharing controllers across different customers, different microclouds, also distributed around the world in places where having hardware is cheaper. For example, we could have controller nodes in the US, in Europe, serving customers in Chile, in Argentina, or in African countries, or countries where costs of infrastructure are still really high. So this means Openstack controller components as a service. So we will be having multiple geographically distributed nodes containing multiple deployments serving different customers around the world. In this way, customers will only need to provide compute, network, and/or storage services, meaning that the initial cost and the investment they have to make to have a cloud running is a lot less than if they had a traditional Openstack deployment in-house. And of course, all of this achieved with the already existing software, mainly with already existing configuration capabilities of Openstack. So here is a general view. We will call each of these customers a microcloud being served by different controller nodes around the globe. So what problems can we have? First, what are the reasons for this? Having controller nodes in places like, for example, in the US or Europe, require a lesser cost than having them in-house. Servers, for example, dedicated servers in cloud providers around the globe can cost around around 30% or even 25% of what the same hardware or even lesser capable hardware is found in Latin American countries. So we're talking that providing controller services from places where we can find more economical solutions can reduce considerably the cost for small to medium data centers in, for example, Latin America, to become introduced with cloud technologies. So we are talking low infrastructure costs, lower operational costs, because making the controller services being handled by a third party will reduce the necessity of the companies to train their own personnel to become knowledgeable of the OpenStack technology that for someone who isn't knowledgeable, it's a difficult process. In Latin America, most of the IT crowd is really familiar with private solutions, for example, with VMware mostly and other cloud providers. But when we're talking about OpenStack, it's still a technology that's not really known by the IT people. So for small data centers, installing OpenStack means capacitation, means probably hiring new people, adding a lot of new costs. And also, we can provide, with this microcloud architecture, an easier deployment using already automation tools already existing in the ecosystem. This can also become a gateway for future local OpenStack deployments. So if I would have a small data center and I want to try this OpenStack, today, of course, you can have these laboratories, these proof of concepts, but what if I want to really try OpenStack and have some customers or some clients of a data center use OpenStack virtual machines? Today, you would need to install a full OpenStack, buy hardware, dedicate hardware that you already have only to fulfilling OpenStack controlling services. That's actually not really the thing that gets that data center money. What gets the money is precisely computing capabilities. So with this alternative, customers can begin transitioning to a cloud environment in a way that's not so difficult to them. And also, it's a nice technical challenge that we will see further because it means having controller nodes geographically distributed in a high latency environment. We will be talking about database clustering through one, using the message queues in a distributed way, high availability. For example, well, here you can say providing high availability across geographically distributed nodes, setting database clusters in high latency, finding a way to redirect messages through the message queue in case of service failure, and also present customers a simple deployment procedure and automate it. So here will be the overview of how will be controller nodes sharing different OpenStack deployments. Mainly, or initially, the common services will be the database and the message queue. In the case of traditional OpenStack deployments, and in our case also, we will be talking about MariaDB and RabbitMQ. But next, you can see that we will be having multiple control services for different customers. So, for example, you will have a Nova API for a customer A living with in the same machine as the Nova API services for a customer B. This will be done. This is thought about using just Docker containers installed through Ansible playbooks. Okay, so first, high availability. Initially, we are thinking about each customer will be assigned what we can call a primary controller node. That will be the one with the lowest latency near the microcloud side. For example, if there is a microcloud in, I don't know, Chile, it probably will have less latency from a controller node located in the US than a one located in Europe. So if we have multiple controller nodes distributed, we will assign one as a primary controller node, and in case of any service failure in that, then the traffic will flow to the next one with the next higher latency. That will be all of these backup controllers. So that generates two questions: how to handle individual service failures and how to handle complete node failures. So in this high availability discussion, first we have what is called a DNS failover. So first, the idea is you will have a customer. The customer here means the microcloud and the end user will access the control services through a DNS record that will redirect to the closest data center. In this case, for example, a customer located in Latin America will probably access the customer US microclouds. That will serve the US controller node or the US controller cluster. But in case of failure, there are now a number of DNS providers that provide this failover system. This can be done through different techniques. If you want, you can look it up more up. You have a unicast, you have anycast. This of course presents a number of issues, and it's of course not the ideal solution to failover and backup techniques. We'll look further that in the next slides. But the main issue here is DNS cache. So most of, from browsers to internet service providers, cache DNS records. So in case of failure, the time between the client gets access to the backup node can be higher than even the time to live established in the record, because most ISPs and browsers do not fully respect that parameter, that configuration. So the question is, why not have a central load balancer, have all requests go through that to access the servers? Of course, latency. If you have, the idea here is to reduce all possible latency between the customer and the controller. So if you put a load balancer in a central place, of course, you will have added latency and will lose that benefit of being closer to the controller location. And of course, you also have the problem is a single point of failure. If the whole, here we are thinking what happens if the whole controller node fails, or the whole controller cluster fails, because we can also think that each individual controller can be an individual cluster for more reliability and availability. So if that whole zone fails, we need to have a way to redirect traffic, redirect flow to the backup service. And as of now, DNS failover is a system that complies to that solution. So now we have service failover. What does this mean? This means what happens if a service in the controller fails? What if, because of any reason, the Nova API fails? Okay, so then in each controller services, we will have a load balancer. In this case, we will be talking about HA proxy. And it can be configured so that if in any case that any of those services fail, you can redirect to a service located in one of the other controller nodes, providing that high resiliency against failures. So services can be configured as backup. So they will only get in traffic if the service in the primary node fails. And you can also configure so that the traffic redirects to the primary node in case the service comes back up. Because one of the problems usually of having backup services in a load balancing context is what happens when the primary node goes back again. What happens with that flow? It still flows to the secondary nodes, having a higher latency in this case, or we can also configure it so that it comes back. So whenever the node or the service goes back up, the sessions that are connected to the backup service are closed and traffic is redirected to the primary server. Also, you have the capability of adding load balancing features. So what happens if my primary controller node has a really high CPU utilization? I want to relocate traffic in cases where services can handle that. For example, Nova API, there's a call to Nova API. I noticed that the server is on the top of its capability. Okay, let's move that traffic to another one of the nodes, adding, for example, like custom health checks. Here is an example in the case of HA proxy, a configuration where you can see that you can mark, that you can configure services, or servers in this case in HA proxy context as backup, but you can also have the possibility of setting primary nodes so that when they are back up, they shut down backup sessions. You also have a lot of more possible configurations that are present in the documentation of HA proxy in case you need to do like some more fine-tuning. What about the database? Okay, so OpenStack usually runs on top of MySQL or MariaDB. So let's talk about MariaDB Galera cluster. Why? Because it promotes native one cluster support. It's done to work in high latency environments. It provides a lot of configuration capabilities to set up the cluster in a way that it supports high latency. There's no use of distributed looking. Of course, you have also the benefit that it has built-in encryption. You can configure network timeouts to tolerate the one outages. You can configure timeouts according to the latency, the specific latency between each server. For example, increasing keep alive timeouts to prevent like cluster partitioning. Here's a configuration example where you can you increase keep alive and inactive timeouts, so tolerate, for example, 30-second connectivity outage. You can also adjust periods and timeouts to be higher than the highest round-trip time measurement between nodes. So you can measure the latency and fine-tune your cluster in the one to support that latency to minimize the possibility of partition and to improve performance. There's another example of configuration. Of course, to take RTT measurements, it's just you can just do some ping between the nodes. I'm sure everyone here knows how to do a ping, but it's never bad to remind it. So here you can see, like, for example, you have a maximum round trip in this case from one node to another, about 12 milliseconds. Let's say if all of that in all nodes it's the same, you're talking that you will need to, you can set timeouts in a value higher than that. So what happens if each of these different controller nodes is in itself a cluster? How can I differentiate in the cluster what nodes are closer? Well, you can do that in Galera cluster. You can group nodes by physical proximity, optimizing the message sending between data centers across different regions. For example, if I have a cluster in the US and it needs to send data after a transaction commit to a cluster to the nodes in Europe, there will be only one message sent between one node and the other, and then the node in the Europe region will send that message to the rest of the nodes in that place, minimizing the traffic so that each node doesn't have to send the transaction commit to every other node in the planet. Just send it once and then relaying the task of relaying that information to the node in the other zone. The same for snapshot transfer and incremental or state. We'll use a donor inside the same data center. That means, like, if one of the nodes goes down and then comes back and wants to synchronize with the rest of the cluster, the donor, which is the node that will give the information necessary to get back in sync, will be the one with the closest proximity. Okay, so let's talk a little bit about the message queue. In the case of the architecture we're talking about, we're sharing a message queue across all services. How to do this? Well, in this case, we're talking about RabbitMQ. RabbitMQ provides the multi-tenancy support through what they call virtual hosts. Virtual hosts are currently supported in Oslo messaging. That's the library that all OpenStack projects use to communicate to the message queue. So we can say that it's totally possible to provide different virtual hosts that will be different tenants for each one of the different microclouds being served. So how to handle service failures? So one of the services in node A fails, and the traffic will be redirected to the other node. Okay, but what happens with the messages, the transient messages in the message bus that need to arrive to the other node because the current consumer is down? RabbitMQ proposes, has a solution that is called the federation plugin that can federate two things, exchanges and queues. Here we will be talking about queues. The idea is relatively simple. You have an upstream server and a downstream server, or multiple. So for each node, you can configure different upstream servers that will relay messages when they receive it. It's not total replication, because that would generate duplicated messages and duplicated processes and duplicated consumptions. The benefits of federating queues is that if you have two nodes and the message is on one node, but the consumer is on the other node, the message will be transferred and the consumer will consume the message in the message queue. But if there is no consumer if the consumer is only on the current node, the message will not be relayed to the other node, preventing message duplication. So the objective here is that the message will be only processed once and not replicated across all the different nodes, generating duplication consumption that may generate duplicated remote code procedures and generate a whole lot of problems. The configuration here is done by policy, so you have different message queues with different names. You can set up named using a regular expression to match the message queue name, to tell RabbitMQ, okay, I want all these message queues that match this regular expression to relay messages in case you have no consumers and there are consumers in the other node. So in this scenario, initially it will be enough to federate all queues using wildcard policy. You will only have to worry not to federate the RabbitMQ ones that use for administration. So here's another example. You have two policies with two regular expressions that match log queues and audit queues. You can set different upstream depending on the policies. For example, if I want to relay the log queues to the nodes in one zone, and in this case the audit queues to nodes in other zone, you can perfectly do that. So diving more into the configuration issues, you need to enable a certain level of plugins. You need to define the upstreams, define the policies. For example, here we see that we have we declare an upstream. So the concept of upstream is the following: each server has a number of upstreams. So a server A, you go to a server A and you declare as an upstream server B, server C, server D, so that when messages arrive in server B, C, or D, will be relayed to this server A with the considerations we previously defined. In the case here, you can see that there's a policy. Well, in this case, the policy is set to apply to exchanges, but the idea here is to apply to queues. The main definition is that in the case of exchanges, it works more as a replication tool than with in the queue federation. The idea is that the message will only be consumed once. Okay, so before this, why are we using federation? Why don't we just use our classic message queue cluster across nodes? Because, well, the simple answer, because you can't. Message queues, in this particular case of RabbitMQ, the documentation says directly, please don't use clusters through wide area networks or environments with high latency, because partitioning happens really, really fast. So we needed to find a solution or a workaround to maintain a certain level of state between queues in case of service failure. So let's talk about deployment. Well, the best way we have found to deploy OpenStack in any case is through KollaHands-on. So if you haven't checked KollaHands-on, please do so. It's a great project. It allows you to automate the process of deploying and allows you to configure really finely all the services that you want and in what node do you want it. So you set an inventory file where you can set up, for example, I want Nova to be in, I don't know, you can say that the compute services and control services, I want them in this type of nodes that correspond to this concrete IPs. I want the networking services to be in these other nodes. So you can group services in a really easy way that allows you, for example, in our case, you just had it in an initial approach is just to change the order of the inventory, and the services will be deployed in this case in the different places. For example, in the traditional OpenStack deployment, where you have network services usually in the control near the controller nodes, or in some cases even co-located with the controlling nodes. you just need to change the location where you want that services installed. In this case, we would want the network, compute, and in some cases storage installed in the nodes corresponding to the customer, to the microcloud, and the controlling services, and also in some cases services, the monitoring services, telemetry that will translate to Gnocchi, to Sailometer, to Panko, etc. So today it cannot actually handle multiple OpenStack deployments. Kolla deploys OpenStack services in Docker containers in the machines, so it's easy to configure them just to add, for example, a prefix to differentiate containers from one deployment to the other, and each deployment can have its proper configuration file, its own inventory, so you can have today multiple OpenStack deployments collocated in the same machine. For example, a Docker container for Nova API, for Neutron server, for any services dedicated to serving one customer, and the same dedicated to serving other customers. Okay, so let's talk about future ideas. There was a couple of talks during the week about Apache Cupid. That's a message queue or something like a message queue that implements AMQP 1.0 standard, if I'm correct. That allows you, that functions different from a traditional broker message queue in the way that it sets up what we can call routers in the place and routes the message considering the shortest path, considering that what happens is that to evade the possibility of having the messages to traverse from one edge to the controller and from the controller back. So we can have cases in which the compute services with networking services can want to talk through the message path, but we don't want that message to traverse completely across the globe to just be relayed back. So transitioning from Federate queue to this Apache Cupid and installing one of the routers in the microclouds could solve us and could reduce even more the latency problems in communication between services. There's also the possibility to add load balancers in the microcloud. So today we have load balancers directly in the controller. The petition goes from the client, from the microcloud, from the compute services, from, for example, Chile, to directly to the node in, for example, the US, and then it's balanced and it analyzes which services are up. But in case it wants to access some information, but in the case that one of those services is down, or some services can be analyzed in the microcloud to reduce all of this flow from Latin America to the US and then to Europe in case a service in the US fails. We can add load where we can analyze the possibility of directly adding load balancers in the microcloud to handle some load balancing between certain services. Also, the idea of sharing more services. For now, we are talking about sharing the database and the message queue, but we can also be talking about sharing Keystone, for example. How can Keystone handle different deployments in the same database? Reducing the idea would be, of course, to reduce the overhead and use the data space used by all these services. So there is the possibility of sharing services, but has to be analyzed, of course, to see if with today's state of the code it can be done, or what changes should be needed to share services across different deployments. Because we need to provide customers with different, we have to assure clients the isolation of the services, isolation of the information. And of course, as I said at the beginning, this is just an idea we have been tinkering with. There's no definite solution yet, so if you have any idea, any recommendation, please just let us know. So thanks a lot for coming. I know it's 6 o'clock in the afternoon, in the last day of the Openstack, so having you, at least like a couple of people here, makes me really happy, so thanks a lot. Of course, if you have any questions, you can ask them now, or you can send me an email, and I'll be gladly to talk about it. So, thank you. Any questions? No. No, but for the sake of the people watching the video, thanks.
So how much do you think you will have the savings in percentage when you split the controllers versus the local deployment?
I don't have fixed numbers, but it's considerable. For example, you reduce the need to buy additional hardware. So considering that, you can be talking, if you're talking about small cloud that carries a server that locally can go up to, for example, $1,000, if you're talking like really small deployments, can be rented for $50 a month in countries like the US or in places like Europe that also provide the same capabilities hardware-wise than the ones you can get locally. The difference in price, especially in the Latin American market versus markets like the US, is enormous. So we are talking the clients getting, if the idea of this is to focus on existing data centers that already have compute hardware and that they have already hardware that they dedicate to compute capabilities, what we are talking about is that they will almost have to make no initial investment to install an Openstack cloud locally, to present their customers private or public compute capabilities and also storage capabilities in some cases.
They can start small.
Yes, the idea is to start small and to introduce cloud technologies in places like Latin America, because the biggest barrier of entry is money. It's always money. So the idea is to let them know that OpenStack exists, that cloud technologies exist, implement them with a low cost, and allow them to use its services and that provide cloud technology or cloud services to their customers for a low cost, so that then afterwards, seeing the benefits that it gets to the company, they may move toward a full OpenStack local deployment on site.
All right, thank you.
Thanks.
And is this a kind of POC or is it the production?
No, for now it's as a POC. We have experimented with it. We have deployed in this architecture, sharing. In our experiment, we used virtual machines in Amazon as controller nodes and local nodes functioning as compute nodes, and it works. Of course, there needs to be fine-tuning, mainly in regards to the message queue communication. There was no trouble in database clustering. That's a problem that's mostly through fine-tuning. You can solve it quite adequately. The message queue generates some problem because there's a lot of messages across the different services. So there's a lot of RPC calls. There's a lot of metric sending, information sending, broadcast messaging. And with an increased latency, you could experiment some issues there.
And how long does it take for starting a server? I mean, what is degradation in time comparing with
for the end
traditional OpenStack?
For the end user, it's not perceivable because the servers, the compute and network services are collocated in the data center, are collocated in the microcloud. So the big delay goes across the end user to the control service, the control plane, and then back to the compute node. So it's a latency considerable when you are talking about message between services, but when you're talking about the end user, for the experience of the end user, like starting a VM, it's the same as the traditional deployment. Yeah. Okay. Okay, thank you very much.